This is section 9.5, Pascal's triangle. We will only be spending one day on this section. Pascal's triangle provides a useful method for raising any binomial to a non-negative integral power n. Now, of course, that sounds so complicated, but it's really not. Binomial is just, when you have two terms, an x term and a y term, for example, or an x term and a constant. That's a binomial. And all an expansion is, a binomial expansion is when you raise a binomial to a certain power. So this, for example, is a binomial. We have x is one term and y is another term, and I'm raising it to the 0 power. So obviously anything raised to the 0 power is 1. And when I raise something to the 0 power, I get only one term. We're going to see why we're writing the number of terms in just a second. Here's another binomial expansion. X plus y is my binomial, called binomial because there are two terms, x and y. I'm raising it to the power 1, and x plus y raised to the power 1 gives me x plus y. And that expression has two terms in it. If I raise the binomial x plus y to the power 2, or I square it, I get x squared plus 2xy plus y squared. And that, of course, has three terms. And now I'd like you to do the following multiplication on your own. X plus y cubed. X plus y cubed. And you'll realize that's a bit tedious, but there's a reason why I want you to do it. So pause the video, calculate x plus y cubed on your own, and then resume. Alright, so you should have gotten for x plus y cubed the following expression: x cubed plus 3x squared y plus 3xy squared plus y cubed. And all you needed to do is distribute the x plus y with the trinomial x squared plus 2xy plus y squared, and you would get the same thing. And we can see that this expression has four terms. Alright, now one more time, and this will be the last time that I want you to do something the long way in this lesson. Calculate x plus y to the fourth. X plus y to the fourth. And a little hint is you can use the result you got for x plus y cubed and just multiply that in turn by x plus y, and you'll get the right answer. So pause the video, do that, and then resume when you have an answer. Alright, you should have come up with this. X plus y to the fourth power equals x to the fourth plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the fourth. And that has five terms. Again, we're going to see in a little bit why we're telling how many terms, because we're going to recognize a pattern. But for now, let's just put this lesson kind of in a context. First of all, we've seen by doing x plus y cubed and x plus y to the fourth by hand, we've seen by doing those by hand that this is tedious and laborious and downright nasty, if you like. But that's the reason why we're doing today's lesson, because good old Blaise Pascal, our brilliant philosopher and mathematician, French philosopher and mathematician, he noticed a pattern in doing binomial expansions. And you may wonder, well, was he just sitting home on a rainy day doing binomial expansions for fun? I don't know. Maybe he was. Great math minds find those sorts of things fun. So maybe he was just doing a whole bunch of binomial expansions. And the brilliant insight that he had is he noticed a pattern. He noticed a pattern. And thanks to his pattern and what we will discover as Pascal's triangle, thanks to his triangle, it's much easier now to do a binomial expansion. Alright, let's continue. This time you don't have to do it by hand. I'm just giving it to you. X plus y to the fifth is x to the fifth plus 5x to the fourth y plus 10x cubed y squared plus 10x squared y cubed plus 5xy to the fourth plus y to the fifth. And this has 6 terms. All right, so let's see how many patterns you can notice. I want you to pause the video, write down whatever patterns you notice, and then resume when you've done that. All right, you probably noticed that each expansion has n plus 1 terms. So for example, in the very first one, the n is 0. There's one term, 0 plus 1 is 1. Next expansion, the n is 1, and there are 2 terms, 1 plus 1 is 2. The next expansion, n is 2, there are 3 terms, 2 plus 1 is 3, etc. Also, the exponents on x decrease from n to 0 in each line, while the exponents on y increase from 0 to n in each line. So let's see that at work in one of these lines. For example, in this line where I'm doing x plus y cubed. Well, if I look at my x exponents, they go down from 3 to 2 to 1 to 0, because x to the 0 is just 1, so that's why x doesn't show up. But we see that decreasing pattern, 3, 2, 1, 0. And we see an increasing pattern with the y's. So we start with y0, which is just 1, and then I go from 0 to 1 to 2 to 3, from left to right. The y exponents are increasing. Another pattern that you may have noticed, the sum of the exponents on x and y in each term is equal to n. All right, let's look at this line, for example, x plus y to the fourth. Well, the sum of the exponents in the first term is 4, because the y exponent is 0, the x exponent is 4, 4 plus 0 is 4. Here, the x exponent is 3, the y exponent is 1, 3 plus 1 is 4. Here, the x exponent is 2, the y exponent is 2, 2 plus 2 is 4. Here, the x exponent is 1, the y exponent is 3, 1 plus 3 is 4. And here, the y exponent is 4, the x exponent is 0, 4 plus 0 is 4. All right, so these are some patterns that you probably noticed. And the last of them is that the coefficients increase and decrease symmetrically on each line. Now, some of you might have already started to figure out what kind of pattern they show. And if you did, congratulations, that's great. But even if you didn't figure out exactly what pattern they show, at least you should have noticed that there's a balance, a symmetry in the coefficients. Let's start with here, x plus y squared. Coefficient of x squared is 1. Coefficient of xy is 2. Coefficient of y squared is 1. 1, 2, 1. Here it's 1, 3, 3, 1. Here it's 1, 4, 6, 4, 1. Here it's 1, 5, 10, 10, 5, 1. So it's symmetric. All right, well, what does all of this bring us to? The triangular arrangement of numbers below is called Pascal's triangle and corresponds to the coefficients of a binomial expansion. Now let's see what Pascal's triangle looks like, and then I think the first sentence here is going to be clear. All right, this is just the number 1, and it's called the 0th row of Pascal's triangle, the 0th row, corresponding to the 0 power that you raise x plus y to in order to get 1. Then we have the row 1, 1, and this is called the first row. I know it's actually the second row. All right, so this is a common confusion in math. If you start counting with 0, then your first is actually your second. If you start counting with 1, then your second is your second. Okay, well, don't let that confuse you. This is called the first row because that 1 corresponds, the 1 of first, corresponds to the n equals 1 exponent of the x plus y binomial. The next row is 1, 2, 1. This is the second row, corresponding to x plus y to the second power. Third row, 1, 3, 3, 1, corresponding to x plus y to the third power. Fourth row, 1, 4, 6, 4, 1, corresponding to x plus y to the fourth power. Fifth row, 1, 5, 10, 10, 5, 1, corresponding to x plus y to the fifth power. And we see a certain pattern here, and this just regards the coefficients, right? In the last screen, we saw patterns regarding x and y and their exponents, and those are going to come into play again. But for now, let's just look at a pattern which we see in Pascal's triangle for the coefficients of the expansion. Each number in the interior of the triangle is the sum of the two numbers immediately above it. And if you pick out any number that's inside the triangle, so I'm excluding the ones on the border, any other number in the triangle is the sum of the two numbers immediately above it. So, for example, that 10 there is the sum of 6 and 4, which are above it. Or this 3 here is the sum of the 1 and 2 that are above it. And so once you have the first few rows of Pascal's triangle, you can construct it indefinitely to, 100th, 200th, 1000th row, because this pattern is going to be consistent throughout. So the numbers in the nth row of Pascal's triangle are the coefficients for the binomial expansion x plus y to the n power. Now this is the full triangle, and you should copy this down. And you're going to need to build on it a little bit. This has from rows 0 to 7. This screen has rows 0 to 7 of the full Pascal's triangle. And the reason I'm calling it the full Pascal's triangle is because not only does it have the coefficients, and we see those numbers in blue, but it also has the x, y terms, which follow the pattern that we identified in the first screen. Let's look at those again. See how the x here is a power of 1, and the y is a power of 1, and the number of terms is n plus 1. Same with here, number of terms is n plus 1. This x has a power of 2. The y next to it that you don't see has a power of 0. 2 plus 0 is 2. This x has a power of 1, y 1, 1 plus 1 is 2. This y has an exponent of 2. The x exponent that you don't see is 0. 2 plus 0 is 2. All right, so we see these patterns that we already identified in the first screen. So those, a lot of times in Pascal's triangle, are not written because people just assume them. But for your benefit, I've put the fully written out Pascal's triangle on this screen, and you should keep it somewhere safe because you're going to need it to build on the base of this triangle a little bit later in today's lesson. All right, so copy that down fully. Next example, use Pascal's triangle to expand 2a plus b to the fourth power. Now, notice that 2a plus b does not look like x and y, but it's treated as x and y. And what I mean by that is this is just the first term, the 2a, and this b is the second term. So this 2a corresponds to the x, the b corresponds to the y. It really doesn't matter what's in the parentheses as long as you only have two terms. Okay? We could have a binomial whose first term is 2x squared y cubed and whose second term is just 1. It's still a binomial because a binomial just means two terms. All right, so if we are asked to expand this binomial, 2a plus b, and we're asked to expand it to the fourth power, then I need the fourth row because that 4 and fourth corresponds to the n equals 4 of the exponent. Okay, so I've highlighted in red the fourth row. The fourth row is going to tell us our coefficients, and then all I have to do is fill in the blanks. Okay, so 2a plus b to the fourth, is the same as the coefficient 1 times 2a, which corresponds to my x because it's just the first term. This whole thing in parentheses is my first term. And that whole thing gets raised to the fourth power, plus 4, which I get from Pascal's triangle, times 2a, the whole 2a, cubed, times b to the 1 power, plus 6 from Pascal's triangle, times 2a, which is my whole first term, squared, times b squared, plus 4 times 2a times b cubed, plus 1b to the fourth. And as I can see, this just keeps following the pattern that I already identified. I've got 1, 4, 6, 4, 1 from Pascal's triangle. And then the pattern of exponents follows the pattern of x to the fourth, y to the 0, x, remember I'm using x for 2a, x cubed, y 1, I'm using y for b, x squared, y squared, x, y cubed, x to the fourth. All right, so all we've done is we followed the pattern of Pascal's triangle exactly. And everything after this is just calculation. It's just calculation. Okay, so my next step, 1 times 16 a to the fourth, and that's just what happens when I raise 2a to the fourth. I get 16a to the fourth. Plus 4 times 8a cubed, because 2a cubed, cube the 2, cube the a, I get 8a cubed, etc., etc. And then I end up simply with 16a to the fourth plus 32a cubed b plus 24a squared b squared plus 8ab cubed plus b to the fourth power. And so this is a successful binomial expansion of 2a plus b to the fourth power. Although Pascal's triangle is stated for a binomial, which is a sum of terms, it can also be used to expand a difference of terms. And this is just because subtracting is the same as adding a negative. So you simply rewrite x minus y to the n as x plus negative y to the n. And then you can apply the triangle to the sum. So for example, use Pascal's triangle to expand 3x minus 4 to the fourth power. Okay, so here's a chance for you to challenge yourself. You should pause the video, do this on your own, and resume when you have an answer. (3x minus 4 to the fourth power) is rewritten as 3x plus negative 4 to the fourth power. Okay, that part is easy. And then I am going to treat this 3x as simply x. In other words, it's just my first term. So whatever I would normally do to plain x, I'm now going to do to the whole term 3x. And whatever I would normally do to the plane y, I'm now going to do to the term negative 4. Okay, since n equals 4, I'm going to use the fourth row of Pascal's triangle, and that's where I see the coefficients that correspond to the fourth row: 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. And then I just do my first term to the fourth power, and then my first term to the third, second term to the 1, first term squared, second term squared, first term to the 1, second term to the 3 power, the third power, and then the first term to the 0 power and the second term to the fourth power, fitting in with the pattern we've already seen. And then after that, it's just calculation. And hopefully you got this on your own. It's good to write out your steps so you don't get confused. And the final answer, 81x to the fourth minus 432x cubed plus 864x squared minus 768x plus 256. Another example, use Pascal's triangle to write the first three terms in the expansion of 2a plus b to the 8th power. All right, once again, you can do this on your own. I am going to give you a little hint though. Notice that we're dealing with the 8th row of Pascal's triangle, the 8th row of Pascal's triangle. And so you're going to have to construct the 8th row. I already gave you up to the 7th row. Now you should use what you know about the patterns and simply construct the 8th row yourself. And then you'll have all you need to solve this problem. So pause, do it on your own, and resume when you have an answer. Okay, so this is the 8th row that you should have constructed. The 8th row of coefficients, 1, 8, 28, 56, 70, 56, 28, 8, 1, which I can get just from the numbers above in the 7th row. All right, so I get the 8th row, and then what do I do? Well, then I just apply the pattern. 1x to the 8th plus 8x to the 7th y plus 28x to the 6y squared plus 56x to the 5th y cubed plus 70x to the 4th y to the 4th plus 56x to the 5th y cubed. Now this is just the raw pattern of Pascal's triangle. On all this is showing is the general form. Now your job, which I assume you already did, is to replace the general x with 2a and replace the general y with b to get our specific answer. And when you do that, because we are only looking for the first 3 terms, I replace x with 2a, x with 2a, x with 2a, and I replace the y here, which is to the 0 power, so we don't need to worry about it for the first term. But the y here I replace with b, and the y here I replace with b. And notice that I still have 1, 8, 28, which corresponds to the first 3 coefficients. And after this, it's really just calculation. And hopefully you were able to get this also on your own. 256a to the 8th plus 8 times 128a to the 7th b plus 2864a to the 6th b squared. Notice just a little, quick Algebra 1 and 2 review. This 2a, the whole thing is raised to the 8th power, so that's why 256 is 2 to the 8th, a to the 8th. 2 to the 8th, a to the 8th. 256, a to the 8th. And this 2a to the 7th power is 2 to the 7th, a to the 7th. 128, a to the 7th is 2 to the 7th, a to the 7th. And the same here, 2a to the 6th is the same as 2 to the 6th, a to the 6th. 2 to the 6th, 64, a to the 6th. And finally, my final answer, 256a to the 8th plus 1024a to the 7th b plus 1792a to the 6th b squared. All right, so hopefully you've enjoyed Pascal's triangle a little bit. Some students like it because it's kind of a cool pattern. And it's certainly easier to expand binomials, especially when you're dealing with, powers of 8 or higher. Certainly easier to use Pascal's triangle than to just chug through it all by hand. Here's the homework. Actually, it's the classwork. The classwork is page 688, 21, 23, 25, 31, 37, 39, 43, and 51. And we'll see you in class.